here with one-way ANOVA, we are only looking at one other source of variation other than the residual variation. With one-way ANOVA, we look at only one other source other than the residual variation. But I just want to talk about maybe some of the more complicated ANOVA that exists. And we won't worry about actually carrying those out by hand. But in case you're ever faced with data that lends itself to that, at least you'll say, oh, I think I heard about this. And then you can look up a little bit more into it. So one is the one-way block design. And our sources will be between the treatments. Between blocks. And then our residuals. Residual or the within groups. Okay. And then you get degrees of freedom, sum of squares, etc., etc., etc. Degrees of freedom, sum of squares, and then mean squares. So you're going to have, the mean squares is going to be, I'll just write. This is the sum of squares for the treatments divided by the sum of squares of the residuals. This one's sum of squares due to the blocks divided by sum of squares residuals. No, that's not the mean squares. That's my F ratio. All of these, I apologize. This is degrees of, mean squares is always sum of squares divided by degrees of freedom for that. Okay. Mean squares treatments. Here I'm going to mean squares errors is also another way of mean squares residuals. Okay, and then you'll have two different p-values. Okay, you'll get a p-value for this F statistic and a p-value for this F statistic. Okay, every time you calculate F statistic. Alright, so what is a one-way randomized block design? Okay, so here I kind of wrote up the table showing you kind of where we arrive even before I told you what we're doing. Okay, with a one-way randomized block design, we're still interested to know if this one variable, whether it's the different diets that the lambs are receiving or whatever else might be going on, we're still interested to see if there's a difference between the different groups there. Okay? But there's something going on in our experimental setup that we can't control or we can't really avoid, and we have a suspicion that this is going to affect our results. Okay? So one of the examples that the book talks about is maybe maybe you want to observe some plants growing. Okay? And maybe you're using I don't know, different fertilizers here, right? So you got fertilizer from company A, fertilizer from company B. You got a control group that has no fertilizer. You got several different groups. That's what you're interested in. You're interested in the effect that the fertilizer has on the growth of the plants. Okay, so the growth of the plants is measured numerically. Everything ANOVA requires a numeric variable, right? And then what you're interested in is if the different fertilizers has an effect on the plants that grow. Okay? But there might be something going on that you can't control. Okay? So maybe you're growing these plants in a greenhouse or something, in some lab, and you're trying to control for all these different factors, make sure that all these plants are receiving are as similar as possible in terms of their environment, with the exception of the different fertilizers. But maybe there's something you can't control. Maybe like the sun rises in a certain way, and maybe another building casts a shadow on some of your plants, okay, and it doesn't cast a shadow for some of the other plants, and there's nothing really you can do about that. Okay. So let's say, this is our greenhouse, and we've got plants growing all over the place. Okay. And let's say this half of the building, there's a shadow, okay, during the day, and this half is constant sunlight. Okay. And we have a suspicion, okay, or we've got a feeling that that's going to make a difference on the growth of the plants. Okay, so we feel like, I'm not going to rebuild my greenhouse. Okay, and there's nothing I can really do about this. So we want to take this into account when we do our analysis. Okay, so this is not, we're not really interested in the effect of shadow versus constant sun, but we got to take this into account when we do our analysis. And so what we want to do is we want to set up our blocks so that each block receives all of the treatments. Okay? What we don't want to do, we don't want to put all of my control group into the shadow area here, and all of fertilizer A into constant sun, and then fertilizer B ends up getting a mix between the two. Okay? Because if that happens, and I find out that the control group grows the least of the plants, I don't know if the reason why the control group grew the least was because they were in the shadow or because they didn't receive any fertilizer. Does that make sense? So if there's something that we can't really control, or something that we just want to take into account, we set up our blocks in such a way that we can distinguish the two. Okay? So here I want to make sure, so a bad setup would be to put all of the control plants into the shadow section. Okay. And again, that's because in the analysis, if I notice the control plants didn't grow, I don't know if it's because they were the control group or if it's because they were in the shadow. So a good setup would be put each fertilizer type or I should say put each treatment, so put each treatment into each block. Shadow and sun. And then we would set up our ANOVA analysis to take into account the effect that might be due to the blocks, and also the effect that might be due to the different treatments. An okay setup, so not as bad as bad setup, but not as good as the good setup, would just be randomly assign all the treatments. Okay, just a pure random assignment. With pure random assignment, it's possible that I still end up with all of my controlled plants in the shadow group, okay? It's less likely, but it's still possible. So the blocked design, we manually force each block to have all the treatments. So that's a one-way randomized block design. That's where there's one grouping variable that we're still interested in. Okay. And then it just gets more complicated from here. Alright, so I'll just briefly mention two-way factorial. Two-way factorial, now we've got two different variables that might affect the treatment. Okay. Or not affect the treatment, two different variables that can affect our outcome. Affect the response. And we are also interested in the, quote, interaction between the variables. So what's a good example here? I can't think of an example off the top of my head, but there could be a situation where we've got different variables, okay, two different variables, and so we are interested in the effect due to variable 1, the effect due to variable 2, and then there's something called an interaction effect, where maybe the two variables somehow, when they're set up together, you get it either magnifies or cancels out the overall effect, and I can't think of an intuitive example off of the top of my head. Well, I don't know. Let's say you were interested in weight loss or something. Okay, you want to see what's going to affect weight loss, and so so some people, they do dieting. Okay, so that's one variable. We want to know what's the effect of diet due to weight loss on weight loss, and then we'll say what's the effect of exercise on weight loss. Okay. And then we'd be interested in the interaction, okay? And I think with diet and exercise, I think the effects are additive, okay? Meaning that if you go on a diet, maybe the effect, if you compare one diet versus another diet, maybe under one diet you're going to lose like 2 pounds, okay? And then maybe if you look at, no exercise versus exercise, maybe with those who are on exercise, they lose an additional pound, okay? So I think with diet and exercise, I think the two things just add together. So if you have somebody who does neither, they're going to lose 0 pounds. And if you have someone who does both, they're going to lose 2 plus 1, a total of 3 pounds, okay? But sometimes there's variables where the two variables, when they line up in such a way that it's not just 2 plus 1 equals 3, it's like the two things somehow magically work together and cause an even greater change than what you might expect if you just added them together. Okay, and then other times, two variables might work together against each other, where you're expecting, maybe those who did the diet to lose 2 and those who did the exercise to lose an extra 1 pound, but then for whatever reason something goes on and they cancel each other's effects out. Okay, we can detect those types of things with a two-way factorial design. Okay, so we can understand the interaction between the variables. Okay, rather than just additive effects. Because a lot of times when you have different variables, the effects just add on to each other. But sometimes there's an interaction and it either grows or decreases in an unexpected way. Okay, I know I'm going long here. I'm thinking of just kind of powering through for a little bit more, and then I'll just let you guys go a little bit early. Okay. All right. So let me. I'm going to pause the video right here.